Continuing now with the section 5.1 notes, we're on page 3. We'll now look at the topic of coterminal angles. This actually is another topic of quite a bit of importance as we look more closely at the trig functions later on. Two standard position angles are coterminal if they share the same terminal side. Coterminal angles always differ by some multiple of 360 degrees or 2 pi radians. That is, if alpha and beta, those are the Greek letters alpha and beta, are coterminal, then either alpha minus beta equals 360 degrees times k, or alpha minus beta equals 2k times pi, or 2 pi times k, where k is some integer. So coterminal angles always differ by a multiple of 360 degrees in degree measure, or 2 pi radians if we're using radian measure. The above equations can also be written as alpha equals beta plus a multiple of 360 degrees, or alpha equals beta plus a multiple of 2 pi radians. You can come up with these alternative forms by simply adding beta to both sides of the equations we have listed above there. That's all you have to do. Let's look at example 3 and we'll illustrate what coterminal angles actually look like. Find two angles, one positive and one negative, coterminal to the given angle. And our first example will be theta equals 60 degrees. So we're going to be working in degree measure. So let's first of all sketch a 60-degree angle in standard position. Terminal side would be about right there. It's quadrant 1. So I'll just write this up above here. Theta equals 60 degrees. Now let's let alpha represent an angle of positive degree measure that is coterminal to theta. And let's say its angle measure is larger than theta. It's a positive angle measure. Then what we would do to determine alpha would be to take theta and we might add 360 degrees to it. Okay, so 60 plus 360 is 420. So an angle that's coterminal to 60 degrees is 420 degrees. That's one that has positive measure. What would that angle look like? Well, what it would represent would be an angle starting from the positive x-axis, going around one complete revolution, and then ending exactly where the 60-degree angle's terminal side ended up. So that one revolution is like adding 360 degrees to 60 degrees. So the total angle measure would be 420 degrees. Remember, we're thinking of angles here more as rotations or revolutions, rotations of a ray about its endpoint. What about an angle of negative degree measure? Well, how about if we take, just a moment, right? If we take beta kind of looks like a bee with a little tail on it, and we take, say, a theta and subtract 360. All right, if you take 60 minus 360, you get negative 300. Well, this angle should be coterminal to theta equals 60 degrees. So we already demonstrated alpha here. Let me just put a little alpha there. Here's beta. Beta would be starting from the positive x-axis. But you see, it would be a clockwise rotation, ending again where the terminal side of theta was originally. So this would be our angle beta. This is what it looks like. It is a clockwise rotation in standard position, but the terminal side is identical to that of 60 degrees. So alpha and beta are coterminal. They're also coterminal to theta, and they do differ by a multiple of 360 degrees. Their difference is actually 720 degrees, and that is a multiple. It's 2 times 360. So it does satisfy the conditions of coterminal angles. Let's look at part B now. Theta equals 7 pi over 4. This is obviously in radian measure. 7 pi over 4, if you look at the circle above, which is not on the screen at this point, but that's about right there, and that's associated with a 45-degree angle. And 7 pi over 4 would actually be this angle right here. So that is 7 pi over 4. You can see where that angle is in the circle shown above, which shows the degree radian relationships we were talking about a little bit earlier. So we want to find angles alpha and beta coterminal to theta. One of the angles we want to have positive measure, the other one negative measure. So let's take alpha to be the one with positive measure. If we take 7 pi over 4 and just a moment. I'm just going to write 7 pi over 4 as theta as I did in the previous example. If we add 2 pi to that, that angle will be coterminal. It'll have the same terminal side as 7 pi over 4. It'll have a positive radian measure. Okay, let me now write this as, this is 7 pi over 4 plus 2 pi. Let's write 2 pi as 8 pi over 4. 8 pi over 4 is the same as 2 pi. We have a common denominator that gives us 15 pi over 4. So 15 pi over 4 is an angle whose terminal side is identical to 7 pi over 4. And that angle would basically be one complete revolution and then another partial revolution to end up with being coterminal to 7 pi over 4. So this would be our angle alpha right here. Well, what about an angle with negative radian measure coterminal to theta? Let's call that beta. Here we could use theta minus 2 pi. And again, theta is 7 pi over 4. We subtract 8 pi over 4, and we get negative pi over 4. That's negative pi over 4. Hope you can see the negative sign there. That angle would be measured from the positive x-axis clockwise, be that angle right there. That would be our angle beta. Basically, you're talking about negative 45 degrees in degree measure. Okay, that angle is coterminal to theta. It shares the same terminal side, but it has a negative radian measure. So we can find other angles coterminal to a given angle by adding or subtracting multiples of either 360 degrees if we're using degree measure, or 2 pi radians if we're using radian measure. We go to page 4 now. Our last topic is that of arc length. We call that if a central angle theta of a circle of radius r intercepts an arc of length s, then theta equals s over r radians. This leads to the following result. It's called the arc length formula. The length s of an arc of a circle of radius r intercepted by a central angle of measure theta radians is given by s equals r times theta. So this is a formula we can use to compute the length of an arc of a circle if we know the measure of the central angle and we know the radius of the circle. The key is that theta has to be measured in radians. So the formula is only, we're only allowed to use the formula if we use radian measure. So if we our given angles in degree measure, we'll have to convert over to radian measure before we use this, this formula. Also, I should point out that the arc length formula is equivalent to how we defined radian measure as arc length divided by radius. All we have to do is take that equation and multiply both sides by r, and that gives us the arc length formula that you see stated right below it there. Let's look at an application of using the arc length formula. Example 4 says Pittsburgh, Pennsylvania is due north of Charleston, South Carolina. That is, the cities lie on the same meridian, the same line of longitude. Those are also called meridians. Find the distance between Pittsburgh, whose latitude is 40 degrees 30 minutes north. So here we're using the DMS notation. And Charleston, whose latitude is 32 degrees 54 minutes north. Use 3,960 miles as the radius of the Earth. So what we have here is sort of a cross-section of the Earth. And what we're saying is Pittsburgh is here, and Charlotte is here, or not Charlotte, Charleston. Charleston is here. This is the radius of the Earth, so we'll call that r. The distance between Pittsburgh and Charleston along the surface of the Earth is the arc length s that we'd like to determine between those 2 points. Okay, and what we also need is this central angle theta. Now that central angle will have to be expressed in radian measure, so we'll have to convert over to radian measure at some point. To figure out what theta is, what we need to do is take the difference in the latitudes. For Pittsburgh, 40 degrees 30 minutes, and for Charleston, 32 degrees 54 minutes. Now, what these latitudes represent are actually these angles right here. This is for Pittsburgh, and this is for Charleston. That's measured from the equator. So the difference in those angles is going to give you that central angle theta. All right, now, because 54 minutes is bigger than 30 minutes and we're subtracting, what I'm going to do is borrow a degree from 40 degrees and write 39 degrees and add that degree onto 30 minutes. Now 1 degree is 60 minutes, so 60 plus 30 is 90 minutes. So I'm going to write that as 39 degrees 90 minutes minus 32 degrees 54 minutes. And subtracting degrees from degrees and minutes from minutes, that would give us 7 degrees 36 minutes. Now, 36 minutes is 36/60ths of a degree. So we could also write this as 7 and 36/60ths of a degree, which in decimal form would be 7.6 degrees. 36/60ths is the same as 0.6. If we then convert that to radian measure, we would have theta equal to 7.6 degrees, and then multiply by pi over 180 degrees. And using a calculator, we would obtain approximately 0.1326 radians. So now using our arc length formula, S equals R times theta, with theta in radians. R is the radius of the Earth, 3,960 miles, multiplied by 0.1326 radians, which, since it's unitless, you don't have to write radians. It has no units associated with it. So our answer is going to be in miles. That'll be approximately 525 miles for the arc length between points P and C. I had to kind of race through that. I hope that that makes sense. I didn't want to go to another video. That concludes the Section 5.1 lecture notes.